about dz over z. So the question was that, well, initially what we did, we defined differential forms, let's say on Rn, but well, it doesn't matter where, as the following. So we said we have smooth functions on M, and then we take a tensor product with, I don't know how to define it, just exterior power of like dx1, dxn. And here we mean the vector space generated by dx1, dx2, and so on, but also by dx1, dx2, also dx1, dx2, dx3, and so on. So we have just this huge dimensional vector space. Apparently, it should have dimension 2 power n, right? I think it's 2 power n. Or 2 power n1 minus 1. No, 2 power n, right? Because we have all combinations of all subsets of dx1, dx2, but also we have 1. Right? So we also have 1 here. And well, so that's our space. And then we can do it on a manifold, or we can do it in Rn. And we have exterior derivative, and we have many things. But if you look at it from the algebraic perspective, so you see what you need, actually, because here in this position, you can put any, I think it's called differential algebra. Right, so you're not differential. So yeah, okay, so better to say like that. So here you can put any algebra. And yeah, I think you also need to have some kind of differential. You need to have the ability to take partial derivatives. And here it's not necessarily smooth functions. So instead of this thing, you can ask, okay, I want to take, let's say, only polynomials. Why not? Or only rational functions. Well, can put here rational functions. So the only thing you need actually is when you do all the algebraic manipulations, that the ability to take the exterior derivative. So if you have a function from this ring, you should be able to somehow to define df. Right, and df, it should be something like this R tensor, something generated by dx1, dxn. Oh, my pen not charging. Well, and then you must have certain operations, well, certain axioms for differentiating, like Leibniz rule. It should be a ring. And well, so, and because of that, we also can consider not only smooth functions times dz, but also we can consider something like 1 over z times dz. And here I mean that, for example, if we are on, let's say, C or a complex curve, we can consider meromorphic functions, right? Because for meromorphic functions, we also can compute their partial derivatives with respect to something. So we can have all the same machinery. Sergey, is it better now?
Yes, of course.
Okay, good. So that does answer your question. Yeah, probably yes. Well, and then there are a lot of there's a lot of algebraic structures on that, and you can study all this stuff purely algebraically. So you may think that you don't have a manifold, you just have certain algebras, and then you do all the same. Actually, you can recover the manifold from this ring of smooth functions. Basically, the idea that if you have all the functions which are zero at given point, which vanish at given point, it's kind of ideal in this ring, kind of maximal ideal. And so if you want to recover your manifold from this ring of functions, you say as well, your manifold just as a set is a set of all maximal ideas. And then you can do the same thing with any ring. You just say, well, it's not kind of geometry on the manifold, but it's geometry over the set of maximal ideas in this ring. And that's very fruitful direction. So the whole algebraic geometry, in a sense, is constructed like that. So you say that, well, if you have a manifold, you have a ring of polynomials, then the ring of like rational functions, if you do it over C, over complex numbers. But you can do also all the same stuff over field of finite characteristic. And then you also have all these like maximal ideas and so on and so on. But your like an underlying space is no longer a manifold. Now it's just certain like algebraic structures, but still you can consider all these differential forms. You can even integrate them. You can construct cohomology, etc., etc. Okay, any more questions about the previous lectures?
Well, you just mentioned about maximal ideal. So what is what you? I mean, I know the definition of the maximal ideal, but what is maximal ideal?
Yeah, here, for example, you just consider any point x, and then you consider all these functions f such that f of x is 0.
Oh, okay.
Sure, because if you have like two functions and their product is 0 at x and one of them is 0 at x. Well, I think that's prime ideal, right? Well, but these ideals, I think, also prime. But well, also they are maximal ideas. Maybe there are more maximal ideas, but still, so given these maximal ideas, you can recover your point x back. So it means that at least the set of all maximal ideas of this ring, this contain the manifold.
Ah, contain the manifold. Yes. I understand.
Well, there are more than these points. So you also, but I think you can also distinguish these maximal ideas from other maximal ideas. Because you can consider the factor by a maximal idea. So in this case, if you consider the space of all functions over this maximal idea, it is R, right? So for example, you can consider the maximal ideas with this property. And then I think that they more or less correspond to points of your manifold. Okay, more questions? Okay, good. Then let me get back to the topic of the course. So first, let's discuss the exercise. Well, for the next time, like a problem that we want to understand the degree of a map between two manifolds. So you have a certain smooth function f between m and n, and these are two manifolds. They have the same dimension, and they also must be oriented, right? Because if manifolds are not oriented, maybe you know that it's difficult to define the degree of the map. And in a sense, the degree is the degree of f is the number of preimages of a point x in n counted with multiplicities. Right, so you have here your manifold 1, here you have a manifold 2, here it's n, here it's m, and then you take any point in n, and then you take all the preimages. Well, so here my preimage is not regular, so here also I ask that the differential at all these points must be not degenerate, so this is not good. So it's better to take a point where all the pre-images are degenerate. And then you consider them with signs. And here the signs, it's simple to understand. So here you have a orientation in N. And so here you also have orientation in M. So in this direction. And then basically you count how many times it goes like in one direction and another direction. And see, so here it will be 0, right? The degree of this map. And then you also maybe prove that this degree does not depend on the point. So for different points, this number is the same. So that's an invariant of a smooth map. But it's difficult to do. So if you define the degree in this way, it's difficult to prove all the things. And much shorter to define the degree in the following way. You just say that, well, if we know that our manifold of dimension n, they have, for example, the one-dimensional nth de Rham cohomology, then in this de Rham cohomology, there is a function to R, which is called integration. So here you have any form. You can just consider the integral over M over this form. And then you know that if you add any other form to it, any exact form, so integral for omega plus d alpha is actually equal to integral over omega if you consider closed manifolds. So let's say that also here it's not oriented, compact, but compact, I think, well, so there's also closed manifold. So closed manifold means that compact without boundary. And then for such manifolds, you have such property. Because if you integrate a form, closed form over a manifold without boundary, compact manifold, you have 0. And so it means that you have this function integration defined on the cohomology classes. And then, so later we will prove that actually this nth cohomology of M that just R. So it means that here there is special form with integral 1, right? So there is this certain form omega 0, such that the integral of omega 0 is 1. So that will be a generator of this. And then you can define the degree in the following way. You just take the generator of, let's say, alpha, omega 0 is generator of cohomology on n, and then you just take pullback of it. Well, just f pullback, right? It's equal to a certain number, let's say k times omega 1 generator of cohomology of, well, so here it's n, and here it's m. And then k is called the degree of f. And well, and now the exercise is to show that it's all correct. What I mean by all correct, that it's this definition coincides with definition of the number of preimages. Right, so exercise to show that the k is a number of preimages. K is equal to the number of preimages. And now let's discuss how to solve this exercise. So what would you suggest if you don't know? But if you know, you also can present what you think. So the question, so you want to somehow relate the pullback of a generator of cohomology of n with the number of preimages. So apparently somehow you need to choose a good generator, right? Because in the cohomology class, you have many forms. And you want to choose one form such that somehow it represents the point. What would you suggest as a form?
Maybe we should choose some form that has a support in the neighborhood of X.
Yeah, exactly. So that's the idea. So first of all, you should show that there is a form whose support is near X. So something like that, right? So you need to prove that such form exists, but maybe it's not very difficult after you learned also today's lecture. But then it will be very easy because since we chosen such a point such that the differential is non-degenerate at the preimages, it means that this small neighborhood actually is diffeomorphic to all these neighborhoods of preimages. Right, and so the pullback of your form is just, it's pullback under diffeomorphism. And so you automatically have a form on this space M such that it's just the same near all preimages, maybe up to sign, right? So you just need to understand what is the sign and how it's related to this count. And then again, if you know this function, this form has support only near this point X, then the same is true about the form on M, right? It also has support near the preimages of X. And then, so it's very easy to integrate it. So here actually are two problems. One problem is how to find such a form. And the second problem is how to understand the sign. So how this integral is related to sign of the differential. And that's actually maybe you need to look at the definition of the integral. So how you define the integration of a form over a set. Okay?
Okay.
I'm sorry, I have a question about this.
Yeah.
Do we know right now that the nth cohomology of the orientable compact closed manifold of dimension n is isomorphic to R?
Not yet, but we will learn it today.
Okay.
Yeah, but you see, so it's kind of, I don't know, there's a style of teaching where everything is interconnected. So sometimes you use things that you prove later, sometimes you, so you do it in another order. Well, today we will prove it. But you see, so to solve this exercise, you can just assume it. So let's just assume that that's true.
Okay.
So and then exercise is reduced to two such like simple questions, like which can be solved without knowing that the top cohomology is one-dimensional. Okay, so now let's go back to some proofs and to something here. Okay, what I want to show, well, so first of all, I want to define for you good covers. So if you have a manifold of dimension n, you can consider open covers, so covered by open sets, and then it's called a good cover if all finite intersections of the elements of the cover are diffeomorphic to Rn. So the picture sounds like that. So you have a surface, and here you have cover like that, right? And then the intersections are all also kind of disks. Okay, and then I claim that each manifold has a good cover. Have you seen such theorem before in any course? Okay, who knows how to prove it? Tell me. Are you here? Can you hear me?
Yes, maybe we should like look at the atlas of the manifold and do something with the neighborhoods from this atlas?
No, I think it's very difficult to prove it like this way. No, at least I don't know how to do it. So the standard proof, it uses the Riemann structure. So the first thing that we have a Riemannian metric on it. Is it clear how to construct a Riemannian metric on it? Okay, so how to prove that there exists a Riemannian metric on it? On any manifold, not necessarily compact.
We can use theorem of Whitney, then deduce Riemann metric from Rn.
But I think the Whitney theorem is only for compact manifolds, or not? I don't know.
No.
No.
That
For
means that there is
paracompact we prove.
Okay.
injective embedding of any smooth manifold into R to n
Okay.
plus 1, I suppose. And then we just need to reduce the metric from the R to n plus
Okay,
1 to
so
manifold.
okay, so that's one way. But also there is another way, which is kind of more standard. You just say that, for example, if you have just two metrics, then their linear combination is also a metric, right? Because the metric is just some quadratic form on tangent space. So then what you do, you just consider the subdivision of unity of one, right? So you have this sum of R alpha equals 1. And then in each small neighborhood, you construct a metric, because for small enough neighborhood, it's just Rn. You just take the standard metric. And then you just multiply your metrics by these functions rho alpha, and then it gives you a metric on your manifold. Okay, that's by partition of units you can do it. So by partition of unity. Well, anyway, there is a Riemannian metric. And then another step is to show that in this Riemannian metric, if you have it, okay, so I can write here maybe. So if you have a manifold M and you have a metric, which is a Riemannian metric, then for a point, if you take small ball, small enough, and this BRX is geodesically convex. So which means that if you take any 2 points inside this ball and connect them by geodesics, then geodesic belongs to this ball. Well, how you prove it? I think you say that so Riemannian metric is just some quadratic form, right? And then in very, very small neighborhood, you can just consider Rn with the same quadratic form. And then up to order 2, it approximates the distances on this small neighborhood. And so if the distance is very, very, very small, then the ball in any metric, in any Riemannian metric in this neighborhood is more or less the same as the ball in well, metric on Rn. And there you know that all balls are geodesically convex. Okay? I think it sounds reasonable. And then you just cover your manifold by geodesically convex neighborhoods. Okay, and then it's good cover, because if you intersect any number, well, finite number of geodesically convex domains, then the intersection is also geodesically convex. And if you have something geodesically convex, it's diffeomorphic to Rn, because it's kind of, something like that, so with all geodetics. Okay, is it clear? So I did not say, I did not prove it. I just explained that, well, it can be proved in this way if you feel all the details.
Yes, it's clear.
Okay. Good. Now, so we know that any manifold has a good cover. And now, so it follows the following. Well, it implies the following proposition that if M has a finite good cover, then its compact cohomology is finitely dimensional. Well, how to prove it? We just need to use induction and Meyer Vietoris sequence. So I just remind you what is that. So, well, when you write the sequences, you have some terms like that. So you have HQ minus 1 of the intersection, and it goes to HQ of the union, and it goes to the HQ of U plus HQ of V, and HQ of the intersection, well, and so on. Okay, and so if you know that all these vector spaces, and actually you remember that all these cohomology groups are vector spaces over R, you know that this thing and this thing, they are finitely dimensional, and you know that the sequence is exact. It's a long exact sequence. Well, I can denote something. Let's say I think that's called D, and that's called well, I. And actually, I can write that the Q cohomology of U and V, actually, that's just the kernel of I plus the image of D. No, it's a kernel of I plus the well, image of I. Okay, and both things are finite dimensional. Yeah, because the kernel, it's contained. No, it's not contained. So, okay, well, what I want to say.
Kernel is an image of D, and the image is finite dimensional by because it's the ball.
Yeah, so this is finite dimensional because it's subset there, but why kernel? Yeah, sure, because kernel, no, wait.
No, kernel is also an image, but it's an image of D because of the exactness.
Yeah, also I can write that it's also the kernel. No, wait. Somehow I become lost. So it was obvious, but now it's not obvious.
Artem is saying that by the exactness of the sequence, the kernel of I is isomorphic to the image of D with this type.
Yeah, you're right. So yeah, that's exact. Sure, we should use it.
Yeah.
Right. So that's, well, since that's exact, that's isomorphic to the image of D, and that's also finite dimensional because it's a subspace of finite dimensional space, right? So it's enough to have these two finite dimensional spaces, and then from exactness it follows that this is also finite dimensional. Okay. So you see, that's very simple because then we can just use it by induction, right? So somewhere we need to use that all these intersections of all the elements of covers are isomorphic to, well, diffeomorphic to Rn. So all the small intersections, they have the finite dimensional cohomologies. And so then when we take the union of them, and so on each step we have that everything constructed on previous step is finite dimensional. Yeah. Right. So because now we can say that induction by the number of elements of cover, by the cardinality of cover. Okay. So now our next goal is to prove the Poincare duality. And Poincare duality, so here it's a formulation. So here we say that Q's cohomology of M, they are isomorphic to the dual of N minus Q's cohomology of M with compact support. And well, that's a standard formulation. You can also write the dual formulation, but it's not always true. So it's not true that if you take the dual to cohomology, it's the same as cohomology with compact support, because of some stupid reason. Well, because usual cohomology of a union of manifolds, they're just a product. So by product, I mean that we can have, for example, what is zeros cohomology? They're just a function, like locally constant functions. And so here, for example, it may be that for each manifold in this disjoint union, we have a non-zero, non-constant function. And so that means that this cohomology of the union of manifolds, it's direct product of them. So you may have non-zero like elements in each term. But if you consider the cohomology with compact support, then you take the disjoint union, it will be a direct sum of them. And direct sum means that we have only finite number of non-zero components. Exactly because of compactness, right? So we cannot consider like function which is not zero on infinite copies, like on infinite number of copies of manifold. So it should be like support must be a compact. Well, and because of that, of some dualities that, well, for finite unions, the sum and the product is the same, but for infinite is not, and because of that, you cannot write this duality in other direction. But well, it's true if your manifold is compact, so well, then just the same. Okay, now let's prove it. So we'll do it as follows. So first of all, we want to define again the integral. It will be pairing between Q's cohomology and N minus Q's cohomology with compact support to R. So here you take any form omega, here you take any form alpha, and then you send them to the integral of omega of h alpha. Okay, then, so that will be our pairing. So this pairing is non-degenerate. Non-degenerate pairing. And that's equivalent to the statement, right? So if you have non-degenerate pairing, which means that for any class which is not zero, there's another class which is not zero, such that the pairing is not zero. Well, that's exactly the statement of the thing. Okay, so to prove it, we need the following. There is a so-called 5 lemma. So, well, it's an exercise. Exercise in the following. So if you have a first sequence, C, D, E, And also here you have A prime, B prime, C prime, D prime, E prime. And then you know that rows are exact. And then the maps, let's say alpha, beta, gamma, delta, epsilon, and then alpha, beta, delta, epsilon, I isomorphisms. Then gamma is isomorphism. Have you seen this lemma on algebra or somewhere?
Yes.
Yes.
Okay. Is it the standard part of the algebra curriculum or what?
Yes.
We the third course proved in course of homology.
Okay, so but anyway, so like two things. Maybe you know it from some place, or if you don't know it, then prove it. So that's the approach. And then now let's prove using this thing there. Poincare duality again by Meyer rhetoric sequence. So now write Meyer rhetoric sequence for both cohomologies and cohomology with compact support. So how to do it? Well, let me try to draw it. So first of all, we have a row for cohomologies, just usual cohomologies. U intersect, well, no, U union V, then HQ of U plus HQ of V, HQ of U intersect V, then HQ plus 1 of U union V. Well, okay, so let's write it like that. And then we do the same below for cohomologies with compact support with a shift I1. And also here you have all the arrows to another direction, right? And here there is a map to HQ minus 1 of U union V. Oh, N minus Q plus 1. Wait. N minus Q plus 1. Okay, now we want to say that, well, if we know the statement that there is a pairing for U and V and for the intersection, then we know that pairing is non-degenerate for the union, right? And so, and we know that the pairing between HQ of Rn, Hn of Rn, and H0 of Rn is non-degenerate. Okay, so let's see what we can do. You want to have here the pairing, which send it to the integral over U and V. And the same is here. So like everywhere we have this pairing to the integral. Okay, so then we also need to say like many things. So first of all, our diagram must be commutative, right? So it means that if we go by diagrams in different directions, like that or like that, then it should be the same. Okay, so it's note that the diagram is commutative up to sign. So what it means that actually when we look at the maps in the migratory sequence, then you see there that we have sometimes signs and so on. Then so it means that actually if you write it here, then it will not be commutative, but it will be commutative up to sign. But that's not very important, right? Because since we care only about non-degeneracy, about isomorphisms, so if sometimes on some parts of your map you have not isomorphism, but minus isomorphism, so in some parts of your space the sign is different, it's not a problem. Okay. Now let's say that, okay, so what we want to show, if we write all that, we want to show that so these things like that. So here, so I mean that we can replace this homology with compact support by their dual spaces. Right, so if you already know that this like taking the integral up to sign, it's the same as taking the dual for the space for smaller spaces, then you want to show this one. So so we need to show the following, so that we have on top we have cohomologies. And here we have cohomology with compact support. And also because of, since we've taken now the dual spaces, now the arrows also go in the right direction. Now, well, finally, what we have to prove, we have to show that it's all commutative and we have isomorphism. So we need to just check each small square on top and see what's going on, because actually the map in the migratory sequence is something well defined somehow. We need to show that indeed it's all commutative. Okay, so how to do it? So let's see. If we have, for example, an omega here on a union. Okay, so let's do it this way. So here we have HQ U and V, HQ of U, HQ of V. And so we have here form omega. Where it goes to the form which is equal to d rho u omega and minus d rho v omega. Right? So that's how we define this map in migratory sequence. We multiplied our form by partition of unity and then take the differential.
Excuse me, but if you take the differential, then the rank of the form changes. But we have a map from
Yeah, you're
homology
right.
to
That means that so here it means we take another square, right? So which square we consider?
I suppose that we take the differential on the map that
Yeah, this one.
from yeah.
Yeah, so here this one. Okay, and now let's see what I want to show. I want to see. Okay, so I need to pair it with some form with compact support here, and look what happens here, right? So also I have a map here. Okay, so yeah, that's from n minus q minus 1 to n minus q. So I want to take a form tau. Let's say, okay, so here I have omega, here I have tau. And I want to say that, okay, so I can put omega here, then pair it with tau, or I can take a push forward of tau and pair it with omega. And I want to say that it will be the same. So that means the commutativity of the diagram. Okay, so and let me draw it maybe here. So that's one thing, and yeah, maybe I draw it just here. So okay, that's a map from the U intersect V, U, U plus 1, right, of U union V. U plus 1, U union V. And here we have H n minus Q minus 1 of the union. And here we map it to H n minus Q of the intersection. Okay, what was the map here? So here, so here we have a form, yeah, but here we also multiplied by the partition of unity. And so here it was a tau. And yeah, I think here it was even simpler. So here it was that, no. Yeah, it was that the rho u v there. Tau. So how we define the this map for the, yeah, I think like that is fine, right? And we will do it like that and extend it y0. Okay, and so now what we need to verify? We need to verify that the integral over omega wedge.
excuse me, I have a question about the map from the usual Taranko homology. Shouldn't be there, like you put a comma there, but there shouldn't be any commas. Like
Yeah.
it's
Yeah.
just minus, right?
Yeah. Yes.
Okay.
Just down. Okay, and that's over U intersection V. And I want to say that it's okay. So let's try to see. I want to say that the same as omega wedge the rho no tau. That's just the same as up to sine omega u d rho v omega h tau. Mm. Okay, that's what I want, right? And so here I want also to use the fact that d rho u tau equals d rho u tau. That's because tau is exact. No, so yeah. So yeah, because it's exact, right? So I consider not just any forms. I consider cohomology of everything here. So I have a sequence for cohomology. So all my forms are exact. So also they are closed. So I know this property for any results. If I multiply my form by a function, I can use this. Okay, and then well, yes, and yeah, okay. So that's what actually happens. I just put the function from here to here, and here there's nothing except that I just position of the differential function changes. Well, so it means that up to sign it's just the same. Okay. So I think that was the square where we have something non-trivial, and on the all the other squares, we have just restrictions, right? So for example, here we have a form on U, form on V, take the difference, or if you have a form on intersection, we get a form on U and V. Right, so here, so also I think it's kind of clear. Okay, let's verify it for this square also. Let's say that here we have form alpha, beta, and here we have form gamma. Right, so what happens here? How you got a form on the HQ? Here we multiply them by the partition of unity and subtract it. Okay, and so here what we did, here just have form gamma and minus gamma. Well, and then you just say that you can partition. Well, you can integrate alpha wedge gamma and minus beta wedge gamma. That's just the same as the integral of alpha minus beta wedge gamma, which is here. Yeah, I think so. In other quadrants, it's just even simpler because all the maps are just restrictions.
Could you please explain one more time about the non-trivial case, the
Okay.
first one square?
So let's
Blue
try.
one.
So we have this. So this square. Okay, another color. So we just want to prove that if we have any form omega here, and if you have any form tau here, and if we just pair them in two different ways, we have this the same result up to sign. Then I try to remember the formulas for these maps, for the maps here between these cohomologies. And So both maps looks like that we multiply form by the partition of unity and then takes differential. Right? Because I know you remember, so since we have partition of units, the sum of all functions is 1. So we have like two elements of partition of unity, let's say u and v, but rho v plus rho u is 1. So the differential of them is 0. And so that was used when we defined this differential. So actually we can multiply by just any of them. And well, so let's multiply it by rho u and take differential on top. So it means that here oh, wait, so here's d rho u minus d rho v. Have we had this one, or we just okay? So let's look. So what we did, because I think I think it's not how we define it. Did we have this one? Or maybe we have just omega goes to d rho u v. Okay, let's look how we define it. Maybe it's better to be consistent. So where is this map? That's from the union. Ah, okay, so it was somewhere here. Yeah. No, it's not here. Okay, so let's see. So also we define a map from, we had to define a map from here, omega k to here. Right, so here you take omega in the intersection. We go here, here, and here. The union. No, again, I've got lost. So how we define this sequence? Let's say here. So what we did, so we have this sequence for each k forms. So here we start with the form omega, we multiply it by this rho u, rho v. And so here we have this map. Yeah, so here it was just restriction. And here it was like that. So we multiplied by rho v, rho u. So here just differential. And now I want to look at the map from here to here. And so what was that? I have a form on the intersection. I just consider the restriction. And I can take the differential. And I take the difference. Well, sum. So, well, indeed, it seems that the map is that omega goes to d rho v u. V means minus d rho v u w. And that's not what I wrote there, right? So, okay, so let's look at how I define this migratory sequence for form with compact support. So here I have form alpha, here I have 2 alpha minus alpha, and here I just multiply it by rho u, rho u. Mhm. And then construct the sequence. Now I have a map from hk plus 1 to hm. So how it was constructed? It was constructed. It also increases different. Oh, wait. Let's go back. Here I have tau, like that, and here I have omega, it goes to this difference. Oh, something strange. See, because when I have the integration, the form d omega disappeared because d omega is 0. But now I have the minus 2. Right, so if here I say that it's, for example, rho v is 1 minus rho u, I can do it, but then I have the constant 2, which is not good.
I think that well, the map in the usual cohomology is okay. I think that something is wrong with like the compact cohomology.
Okay, then let's try to reconstruct it back. So you mean that maybe so here we also should be difference, right?
Yeah, probably there, because I can't see why d rho u multiplied by tau lives in intersection.
Right, you may be right. So let's look there. So how we define it here? So we have a cohomology here. Okay, then how we get there? Yeah, it seems that indeed we should multiply it by the partition of unity and then take d. Right, so it should be the same. Okay. Let's see. So we said maybe here we should take the d of this minus d of rho v of tau, right? And then it will belong to no wait. So it's all strange. tau in the union multiplied by rho u there. Oh, it's fine. And so then instead of one summand, we have two summands like that, right? So we have one with d rho u and another one with d rho v. Maybe I just mistaken with all the maps. No, okay, so here, okay, so here, okay, so maybe it was okay. So here I have v, and then it goes here to d rho u v omega on rho on u, right? And it should be minus d rho v omega on v. It seems correct, right? So it just well, it's not well, it's not the difference. It's that on u it is this one, on v is this one. So actually, I think it was correct. So okay, so let me write it here like that. So v omega goes to d rho u v on u, and minus d rho v omega on v. It's not the difference. Still, is just well this forms. Because on the intersection, that's just the same form. Because on the intersection, it's d rho u v is equal to minus d rho v, like that. Because on the intersection, both of them are defined. Because their difference is zero, right? So the difference of these two things is zero. So actually and the same with tau. If I have tau, right? So tau here just any form, but if I wish to restrict it on u, yeah. So here also when I restrict, so when I have a form tau here, that's a form on the u and v such that on the intersection they're just the same. Right. So well, so let me say it like that. So here, no, I think it was correct. So what I mean here that if I have tau, I can take so this is a map d upper star of tau. If I extend it by 0 to u is d rho u tau. False. That's the claim. So if I want to just look, so what is d tau on u? Then the tau on u is just this form extended by 0. And then it's just, you see, because this is a form in cohomology, and this form is just some concrete form which I can compute explicitly. Just some that's a representative of the D lower star. The upper star. Yeah, I think it's all correct. I lost all, or I still here? Can you hear me?
Yes.
Yeah.
I
Okay,
think
so
it is better to think about it on
I think now it's correct.
my-
So okay, so just look at the definition of differential in the migratory sequence. I claim that in this case, for this map, which is non-trivial, your map is indeed, you just need just one differential like that. Because but there is a lot of notation because you sometimes restrict forms to U, sometimes you restrict them to V, but the key fact is that this d rho omega equals minus d rho omega on the intersection. And so if you look to consider this form as a form on U, you consider this thing. If you want to think about this as a form on V, you consider this thing. And the same with tau also. When you have tau, when you compute the differential, you just multiply it by one of the functions, and then sometimes you extend it by 0. That's how you define the differential.
Okay, that makes more sense. Yes, thank you.
Yeah, and then you see, then since we consider this all in cohomology, you can put this partition of unity out of D. So instead of considering this D rho U W, you just say that it's D rho U wedge W, wedge omega. Right, and then so all this question of commutativity boils down just to this thing that you can change the position of this differential of the partition of unity. I mean, let's look at the definition maybe at the migratory sequence, the initial one. For example, here you see. So what happens? You have a form. You multiply it by this partition of unity, but then when you since your diagram is commutative, so when you just go by differential here and here, you go to 0. So you want, if you want not to have 0, you just keep one of part of it, this one. Right? So you restrict your function, then you multiply it by the. So if you just restrict your function, then take the difference. So you see here, if you take that, let's try to remember it together. So here you have omega, and you can just restrict omega to U, restrict omega to V, and then take the difference. It will be 0. But instead you multiply it by rho V or rho U, and then take the differential. And now the claim is that the differential of rho V omega is equal to the differential of minus rho U omega on the intersection. And so so that will be the image there. So here it goes. Maybe it was written somewhere. Well, so I think that's the definition of, okay, so of the map. So that's this D upper star is defined as I said. So that's map from omega K U H K of U union V to hk plus 1 of u intersect v. It goes like that. So you have a form omega, and you multiply it, goes to d of rho u omega. Or is the same, you can send it to d minus rho v omega. It will be the same. It is the same form. Okay, I think we proved it. One way or another one. Okay. So we have 15 minutes. Let's do the same for other things. So we have also a Q-unit formula. The Q-unit formula is that if you have two manifolds, M and F, then the cohomology of the Cartesian product of two manifolds is actually this product of the cohomology rings. I mean that here the cohomology of degree n is just this sum of these tensor products over R. Well, how to prove it? You prove it exactly the same. You just say that if you have the Mayer-Vittori sequence for M, so you have this HP, U, and V, HP of U plus HP of V, HP of U intersect V, and then HP plus 1 of U union V. And then you can just, so you claim the cohomology of these things multiplied by F is the same as you just multiply the cohomology by cohomologies of F. Homology ring of F. Well, maybe it's not good to multiply by homology ring, so you multiply by just one of them. So you take here n minus p. Okay, so n minus p of F. U plus HP of U multiplied by Hn minus P of F. So, well, anyway, just multiply by Hn minus P of F. Okay, so you multiply the whole sequence. And then you sum over all P. And then you have the following thing. So you have this, and in every term, then sum up by P. Then in every term, you have the following. So you have that sum of HP U V tensor Hn minus P of F goes to the sum. Here you have HP U tensor Hn minus P F plus HP V tensor Hn minus P F. Well, and the same term here, but here it's everywhere you have summation by P. And then, so that's your one sequence, and another sequence. You say that, well, you want to prove that it is the same as here. That's Hn U union V times F, Hn U times F plus Hn V times F, and here that's the intersection. And again, so how you want to prove that if you know this fact for the like two separate things. And for the intersection, then you know this fact for the union. Right, so you already know that for parts, like for like U cross V and U intersect V cross F and V cross F, it's all true, and you want to show that that's true in this segment. So what you do, you need to show that this diagram is commutative, and you already know that this like both rows are exact. And so you just need to define all the maps. Okay, so how you define the maps? So you want to say what? So you have, for example, a cohomology. You have an element, for example, alpha here and beta here. So how to send it here? Well, it's just alpha wedge beta, right? So if you have just two manifolds, the Cartesian product of them, you just send them to forms to these things. Like formally, I think you can say that so you have your manifold M cross F, and you have map to M, you have map to F, and so you send this alpha beta, you send it to, it's a pi1, it's pi2, you send it to pi1 upper star alpha, and wedge pi2 upper star beta. Okay, that's how your map in the diagram is defined, from this red row to the black row. And well, that's the same map everywhere, and you need to show that it commutes with differential. Well, how to show that it commutes with differential? Well, how differential is defined, first of all. So here you see that if you look at the definition above, we everywhere have multiplied by the cohomology of F. So on this part of cohomology of F, differential is defined as 0. Right? So it means that, well, if you compute it here, d alpha beta, it will be just d alpha. Okay, and then you say that, well, now if you after that apply this map, then the question boils down to the fact that differential and pullback commutes. Well, that's true. They commute. Then you should say that indeed it's all commutes with this Meyer-Vittorius sequence. So it means that when you multiply alpha, for example, by this partition of unity element, also it's the same as, well, you can multiply it above and then apply D, or you can multiply it below and then apply this map. Well, and I think also it's kind of clear because, well, how should you think about that? Is that this Unit formula means the following. So usually you consider the forms with coefficients which are, well, functions, and it's all linear over reals, right? So you just multiply by constants, it's just the same. But now instead of constants, you also have this strange Hn minus P of F, this cohomology ring of F. But since you just multiply everything by it, it affects in no way, no cohomology, nothing. So, I mean, the best way to think about this Kunis formula is that just instead of real coefficients, you do all that with the coefficients of cohomology of F. That's just another ring. And the only thing that you need to show that indeed these maps are fine in case of Rn. So indeed, when you have just Rn times F, then the cohomology is just the same as cohomology of F. Well, and we know that we proved that last time that well, these things are homotopy equivalent, so they have the same homology. Well, so it means that if everywhere here you just, you know, in the Meyer-Vittori sequence, you remember that when you have the homology of Rn, you don't have homology of Rn, you have homology of Rn with coefficients in H of F. So that's actually what's going on. So basically, an algebraic way to think about this QNet formula is that instead of cohomologies of Rn, or like manifolds with coefficients in, let's say, R, you have the same with coefficients in cohomology of F. You just take a tensor product with this ring. Is it understandable assumption or not? Because I cannot see your faces. Maybe your faces are not happy. Well, maybe you are not here any longer. Well, let me then say that you can also prove exactly in the same way the Leray-Hirsch formula. Let me just tell you what's that. So here I need to have a manifold M, and I want to have a bundle with a fiber F over it. So locally, this thing is just direct product of M cross F. So it's locally in for every point there is a neighborhood such that there's just M cross F. But then when we go over this manifold, it may be some twisting, like over Möbius band. And then we say that suppose that there are global classes E1, En in cohomology of, well, how to, let's call it E, such that if we restrict them, En to fiber, they generate the cohomology of the fiber. They freely generate the cohomology of the fiber. Then cohomology of E is just cohomology of M multiplied by the vector spaces generated by these classes. So what I mean here is that if there are such good classes over the fibrations, such as the restrictions to every fiber, it's kind of basis, then this QNet formula is true globally, not only locally. So how to prove it? Again, so we just look at the Meyer-Vittori sequence here. We just do all the same. We just, instead of this U, V times F, we consider this, well, part of the fibration over U union V. And then we just say that now, so we just intensify this Hn minus Pf with this part generated by the classes E1, En. Right, so we always can restrict these classes E1, En to any part of our manifolds, and then here it will be the same formula, and here it also will be the same formula. Okay. Maybe not very enlightening. Well, anyway, so let's do the following way. So let's try to read the book, both two, the chapter about that. And then next time we just, if you have questions. If you have any reasonable question, we just discuss it. Okay, so that's all things there. I think maybe like 2 or 3 pages, or maybe 5 pages. And okay.
I
Let's go.
have some question about Kuhn's theorem.
Sure.
The isomorphism in the isomorphism in the first isomorphism that the ring of cohomology of M times F is isomorphic to the tensor product is the isomorphism of vector spaces or the isomorphism of rings. So we didn't check that it preserves the cup product in cohomology, but maybe it does.
Yeah, I think for Kuhn's formula, yes, it preserves the product, the ring product.
For Leray-Hirsch formula, it isn't true, and I know it.
For Leray-Hirsch, well, I think it's not true, because here. So where is Leray-Hirsch? Yeah, it's here. For Leray-Hirsch, I don't think it's true. I think it's false. But I will no wait. Let's see. So that's a reasonable question. I don't know. So because it seems that indeed for Leray-Hirsch it should not preserve the product. But you see, it's very strong condition that there are some global classes such that they, being restricted to any fiber, they freely generate the cohomologies. So in particular, so if you just restrict these classes to the fiber, you obtain the same ring structure. So it means that you can multiply 2 classes and then restrict to the fiber. It will be the same if you first restrict and multiply. Okay, so that's okay. So let's say the questions. Ring structure. Okay, what else? What other questions should you think? Okay, so then let's say that's all for today. So for the next time, I will tell you the pages in the book, but you also can find it themselves, the pages in the book, and try to check what's written there. I think it's more or less correspond to what I say. And ask questions, and then we discuss questions next time. Okay, I stop recording.